Okay. Before I forget, just want to let you know that the calculus textbook has arrived in the media center. If you want to pick up, you can pick up a copy. I just want to say that I don't think you're gonna need a textbook because I'm going to put everything that you need in your packet, and the keys will be on the website. So the only reason that you might want to have a textbook is just so that you have um, a physical textbook at home as a resource if you want to flip through some of the examples. But even the exercise problems are pretty much the same as I pulled the exercise problems from last year. So this is when I first taught from this textbook last year. So I didn't want to, create a whole redo the whole homework assignment because of a new textbook. And I looked through it. It's basically the exact same problems, just different page. So I guess you could work off of the new textbook, but I'm going to be photocopying all your exercise pages in your packet. But Media Center, they just want to have an idea how many students will want a textbook. So you don't have to commit to this, but if you have an idea that you think you want a textbook, if you can raise your hand, you can always change your mind later. You can always, go with the Media Center. They just want to have a general idea. So raise your hand if you feel like you want a textbook. That's fine. I assume that most students are not going to need one or want one. And if you are going to get, or if you pick one up, just leave it at home. There's really no reason for you to bring it into the classroom. Okay, so, but if you change your mind, that's fine. You can always go and pick one up later. And I'll send out a reminder this week that they're going to try to get the textbooks ready for you. And if you want to pick up sometime this week. Okay, but I'll send out a text reminder today or tomorrow to let you know that they're ready and that you can pick them up. Okay. All right, so we're going to start our true first unit. This is a unit on limits. I'm just kind of briefly go over the calendar. The calendar is on that second page of your packet here. So we went through first week. So we're going to go through, we're going to talk about rates of change, which is basically slope. This is kind of like a precursor to what we're going to be doing with the derivative. So we're going to do a little bit of review with that, and then we're going to move into talking about defining limits, finding limits graphically. And then tomorrow we'll look at algebraic limits. That is going to, finding limits algebraically is going to be what's going to take a little bit more time. So we'll do tomorrow and Wednesday to go over that. And then we should be get through everything by Wednesday. We can start quiz review Wednesday, Thursday quiz review, and then Friday quiz just over these few topics here. Starting tomorrow, I'm going to be checking homework daily. If there's homework, most days there will be homework unless it's review day or the day of a quiz or a day of an assessment. So, and everything is in your packet. Sometimes it's AP practice, sometimes it's exercise problems. So in these textbooks, they have exercise problems, but then they also have AP practice. Many of them are just multiple choice questions to kind of help you kind of get accustomed to maybe the way that they could answer or they could ask questions on the AP exam. So yeah, so that's why there's this distinction between AP practice versus exercise problems, but they're all going to be in your packet. Okay, so let's and then I have this being page 0 here. These are important concepts that summary of important concepts that I will highlight for you when we get to reach the end of the unit. All right, we'll do the rates of change later. Let's jump directly into talking about limits. So let's go to page 1. All right, so the limit is the y value that a function or graph approaches. So that's the key word there, approaches from both sides as the x value moves closer towards a given constant. This is different than function value. So function value is the physical location of the point on the graph, but limit is talking more about the approach. I want to kind of talk a little bit about what I mean by that. So let's say we have a graph here, right? We have a f of x here. There's a hole. There's a point, and what's the y value of at x equals 2? So basically, f of 2. What would you say f of 2 is equal to? Just looking at the graph here. F of 2 equals, where's that point? 1. Yeah, f of 2 equals 1, right? We're just zeroing in on where that point is. We don't care about how the rest of the graph looks. We just want to know where that point is. Now, the limit as x approaches 2, it's a little bit different. So we're going to say this. Limit as x approaches 2 of, yeah, this is r here, of r of x is equal to. Now, we're talking more about the approach as we get closer towards 2. So here, we don't really want to look at where the point is. We want to look at more how is the graph behaving or moving around x equals 2. So let's start off with doing this. Let's start off with picking points that are close to 2 on the graph. So we see that there's a hole here at 2, but I'm going to pick points on either side of 2. Because that's the key word here, right? We're going to approach 2 as we get closer towards 2. So I'm going to highlight those 2 points, and I'm going to make both points head towards 2. So right now, this is a point to the left of 2. I'm going to make it go towards 2 along the path of the graph. So I'm going to use an arrow to indicate where that point is headed. On the other side of 2, I'm going to make this point go towards 2 as well. I'm going to draw an arrow along the path of the graph. So now the question is, are those 2 arrows pointing to the same destination? Where's both arrows pointing towards? The hole, right? And where's the value of that hole? 4. Yep. So that's the limit. Okay. So in order for a limit to exist, the graph must approach the same real number, y value, from both sides of the target. So we're going to have a more formal way of representing the arrows, but I think it's nice to start with the arrows because visually it should be obvious, right? Okay, if the arrows are pointing to the same y value, even if that y value doesn't exist, we're going to confirm that's where the limit is. But if the arrows are obviously pointing to different destinations, then we'll say the limit doesn't exist. Okay, so basically, just look at the arrows. If I can convince myself that the arrows are pointing to the same y value, then that's my limit. If not, then there's no limit. Okay. I'm going to talk about that in a second here, but it does need to approach the same real number y value. Now, here's some examples of where limit does not exist. Where the limit doesn't meet this criteria, the graph approaching the same real number. So let's look at example 2. Now, we're going to approach 5. I'm going to highlight where 5 is. 1, 2, 3, 4, 5. So we're going to limit as x approaches 5. So keep thinking about that word there, that we're talking about the approach. So we're talking about limit here. So I'm going to purposely pick points on either side of 5, relatively close to 5. I'm going to draw an arrow towards 5 along the path of the graph. So now, are the arrows headed to the same y value? Is this arrow headed to the same destination as this arrow? No, they're not. So therefore, the limit does not exist. Okay. So we can say limit as x approaches 5 of f of x equals does not exist. Or you can abbreviate it using DNE. Sorry, let me backtrack for a moment here. There's notation that I want us to pay attention to that I'm going to keep reminding us of. The way that we're going to say it is we're going to say the limit is equal to 4, or limit as x approaches 2 is equal to 4. And we're going to forget to say that there's a function here, which is fine if you don't say it, but we can't leave this function out. We either have to have something in place of here, either the expression, or we have to name the expression or name the function, but we can't just leave it blank. So this is the way that we say it, but we can't write it this way. This is not the appropriate notation. Even though we say limit as x approaches 2 is equal to 4, we have to be able to talk about what you're referring to. So we have to reference some function somehow. So either call it r of x, f of x, or whatever the function is named is, or the full expression. Okay? But either way, we've got to have something in place of that. Okay. All right, next up, we can tell there's a vertical asymptote at x equals 3. And now we're going to find the limit as x approaches 3. So again, in order for a limit to exist, we're going to have to start from points on either side of our target. And then we move towards our target and see if the arrows are moving to the same real number y value. So I'm going to pick points on either side of 3. I'm going to head towards 3 along the path of the graph. Just going to follow where the graph leads. So the left arrow is headed towards where? Headed towards what y value? Infinity. How about the right side? Also infinity. So they're both headed towards positive infinity, but is infinity a real number? It's not. So even though we can make an argument that they're both approaching the same y value, it's not a real number. So this also falls under the category of does not exist. Now, having said that, sometimes we may need to give a subcategory of does not exist. So even though the limit doesn't exist, there's a subcategory in terms of talking about the behavior from both sides. So they're both consistently moving towards positive infinity. So we can create a subcategory and say the limit doesn't exist, but the behavior is that they're both headed in the same direction. They're both headed towards positive infinity. That gives us a physical description as to how the graph is looking. But infinity falls under the category of does not exist. Likewise, what if both sides are headed towards negative infinity? Then we'll say the limit doesn't exist and the subcategory is negative infinity. Okay. What if one was going up and the other is going down? Then it obviously doesn't exist. But then if the arrows are not moving in the same direction, then we have no subcategory. We just leave it as does not exist. Okay, this is kind of a strange one. We're not going to see much of this at all, but just wanted to go over this for just to go over this third option. Sometimes you have these strange functions. This is sine of 1 over x, where it oscillates and it just never settles on a y value. So this is a strange graph where no matter how far you zoom in, it's still just going to be a jumbled mess. It's just never going to settle on a y value. So any graphs with the oscillating behavior where it doesn't settle on a y value, that also falls into the category of does not exist. Okay, we can also evaluate a limit looking at a table of values. Right? So these are some order pairs for this function that's defined as x cubed minus 1 over x minus 1. And here we're doing limit as x approaches 1. So we want to choose points close to 1 and move towards 1. So just like how we were plotting points close to our target, we're going to start off on both ends close to 1, but on opposite sides of 1. So you can see that this is approaching 1, right? 0.9, 0.99, 0.999. These are all getting closer towards 1 from the left side. And then this on the right side is headed towards 1 from the other side, right? We're getting closer towards 1. This is basically what the arrow is doing from the graph above. And then you can tell that the graph doesn't exist at x equals 1. But we're talking about limit here, so it doesn't really matter if the point exists. But to find limit, we want to look at the approach of the y value. So do you see what is the y value getting closer to if you just had to make a prediction? 2.7, 2.97, 2.997. That looks like it's getting closer towards what? For the y value. 3, okay. Looks like it's getting closer towards that integer value 3. How about from the other side? 3.31, 3.03, 3.003, 3.0003. Getting closer towards what y value? 3 as well. Okay. So the approach is consistent, even though the order pair doesn't exist or it may live elsewhere. This basically is essentially the same as having the arrows headed towards the same y value. So therefore, we can conclude that the limit is equal to 3, even though the point doesn't exist. Because we're talking about approach. Right? As long as there is consistent approach from both sides of your target, then your limit exists. All right. I want to do 1 through 7 with you, and then I'll have you guys try some of these other ones. Now, there's going to be a mixture of limits and order pair. So just keep in mind, if it's asking for an order pair, we don't care what's happening around that point. We just want to just zoom in at that point. Wherever that point is, that's our order pair. But if we're talking about limit, we have to kind of take a step back and ask ourselves, okay, let's pick points on either side of our target, and then we're going to move towards our target. And can we convince ourselves that the arrows are pointing in to the same y value? If it is, the limit exists. If it's not, then limit doesn't exist. All right, limit as x approaches -5. I'm going to pick points on either side of -5. So on one side, it's this branch. On the other side of -5 is this branch. I'm going to draw an arrow towards -5. Are these both arrows headed to the same y value? They're not. So therefore, limit does not exist. Right, limit as x approaches -4. I'm going to pick points on either side of -4. It's getting a little close here. So I'm going to pick points on either side of -4. I'm going to follow my path along. I'm going to follow along my path towards -4. A little bit hard to see here, but are these arrows headed to the same y value? Yes. And where is it both headed towards? Towards 1. Yeah. Even though the hole is there, we're looking at the arrows. Okay. The arrows are guiding our decision for what our limit is. F of -3. So now we just want to look at -3 here. What is the y value that's defined at -3? -2, right? We see an order pair here. The graph goes right through that point. That order pair is -3, -2. limit as x approaches -3. So I'm going to pick points on either side of -3. Are the arrows headed towards the same y value? Okay, they're both headed towards. Also what? Also -2. All right, number 5, f of 3. F of 3. Do we see anything at f of 3? Anything defined here? There's a hole, so therefore what? Does a point exist? No. So undefined or does not exist. You can interchange them. That's fine. Limit as x approaches 3. So we're talking about the approach here. So pick points on either side of 3. Draw an arrow towards 3. Are the two arrows pointing to the same y value? Yes, they're both headed towards -3. Limit as x approaches 6. We're going to talking about approach again. So pick points on both sides of 6, close to 6, and draw an arrow towards 6 along the path of the graph. Are these two arrows pointing to the same y value? No. Therefore, limit does not exist. I want us to just make an observation. This is more of what we're going to discover maybe in the next few days. But can you make a generalization in terms of why is it that sometimes my order pair and my limit matches very nicely? And then there are other times when my limit and order pair are completely different from each other. Can you make a general observation as to, when is my limit and order pair going to be one and the same? And when is my limit and order pair going to be different from each other? Okay. Okay, you're going along the right path. Yes, but there's a little bit more to it. Anyone else have any thoughts? What is it about the graph that allows an order pair and limit to be the same versus a graph where limit and order pair may be different? Yeah. Okay, where not as a whole, but a little bit more. What if there's a vertical asymptote, right? Something about the connectedness of the graph. So the idea that we're going to eventually come across is the idea that if my graph is connected, right, if there are no breaks in the graph, your limit and your order pair will be one and the same. You're not going to distinguish them at all. But as soon as there's a break in the graph, a hole or an asymptote or a jump discontinuity, then your limit and order pair are going to begin to show differences from each other. So we're going to lead to that idea in the next few days, but I just want to kind of point that out to kind of have you guys look at a graph from that perspective. Right. So here, if you look at this order pair, -3, at -3, there is the graph is connected, right? It's continuous. So if there are no breaks in the graph, there are no distinction between the two of them. But as soon as there's a hole or an asymptote, your order pair and your limit will always be different from each other. Okay, can we try 8 through 15? Let me walk around and see how you guys do, and then we can go over these as well. Again, order pair, you can just go ahead and find your point. This one, Peter. If it's an order pair, you can just go and look at that point. But if you're finding limit, right now, force yourself to draw 2 arrows and then use those arrows to make your conclusion. Because our tendency is sometimes we want to look at a hole and we want to assume that, okay, the point doesn't exist, so therefore limit doesn't exist. But many times when there's a hole in the graph, the limit still exists. At 8 through 15, check your answers. Again, DNE and undefined are interchangeable, so there's. I say undefined for point and DNE for limits, but they're interchangeable. It's fine. Any questions? Okay, go to page 3. Let's see if we can do the full page there. There's asymptotes involved on page 3. Just understand that asymptotes fall under the category of does not exist. But if the arrows are pointing in the same direction, you can do parentheses, positive infinity or negative infinity, as long as they're pointing in the same direction. But if one is pointing up and the other is going down, then we can say D and E. We don't have a subcategory. If a vertical asymptote is not showing the branches both headed towards the same infinity. Okay, 16 through 23. Any questions? All right, go ahead and try 24 to 31. Anybody still need to look at 16 to 23? Any ones you want me to go over with you? Okay. Okay, so great. You guys are not struggling with this. Seems like you understand how limit is different than order pair. Limit is the approach. Order pair is just, does that point exist regardless of what's happening around close to that point? Now, what's a bit more challenging is the next page where the graph will be blank, the properties will be filled out, and we have to sketch a graph that fulfills these expression or these statements. So I want to talk about how we can create a graph using given properties. Okay, so I'm going to help kind of guide your steps for graphs like this. All right, page 4. Let's start off with the easy things. So the easy thing is the order pair. Order pair has no, we don't care what's happening around the rest of the graph. The limit is going to be connected parts of graph. So we're going to have to draw some connected points with limits. But for order pair, it's just going to be a kind of standalone point. So let's go ahead and do some of the easy ones first. I'll do this -5, -2. That's an easy one, order pair. So go to -5, go to -2. Plot that point, and then we're done. Right. Second, limit, f of -1 equals 6, order pair -1, 6. All right, the rest are all involving statements regarding limits. Let's start with the first one here. Limit as x approaches -5 equals 3. So what I'm going to do is, we know that the graph is going to approach this order pair -5, 3, but we're not committing to that the order pair will live at this point. So what I'm going to do here, before I put on the graph, this is what I want to do. I want to put -5, 3. I want to put a hole there. Okay. Sorry, -5, 3. And the approach is towards that hole. So I'm just going to put a hole there and then just have kind of segments that's going to extend from both sides of the hole. Now, it doesn't have to be a hole, but I like to start off with a hole because if I fill in that point, I may have to erase. But if it's a hole, then worst case scenario, I may have to fill in that hole, but there's no need to erase it. So I think having a hole is always the kind of like the safer start. And then if a point is going to be defined, then there's going to be a statement that's going to tell you where to fill in that point. Okay. So whenever I see a limit, I'm just always going to find that order pair and put a hole at that order pair. So -5, 3. But I'm not going to extend my graph too far because I want this to still be a function. So I don't want any overlapping lines that's going to cause vertical line test to fail. So I am going to extend this out a little bit later, but not until I kind of have a better idea where the graph is, how the graph is looking. But at least the 2 segments is telling me, at least I fulfill that condition. I know my graph is approaching that order pair from both sides, but it's actually, in this case, it's really good that we put a hole here because there's a point that is defined at a different y value. So it's actually, this is really the only way that we can do this. But I would say whenever you see a limit problem, just always put a hole and extend slightly in both directions, and then we can discover what's going to happen with the graph later. All right, next statement. Limit as x approaches -3 is equal to infinity. What does that tell you? That there must be a what at -3? Vertical asymptote. Okay, so what we want to do is at -3, you're going to do a dotted line, and you want the graph to do this. Right, it's going to get that the arrows are going to move closer towards your asymptote. Your arrows are going to move closer towards the asymptote. So here's -3. I'm going to put a dotted line at -3. And I'm just going to go towards infinity from both sides. Now, I think this is kind of a indication as to where I want this segment to go. I want this segment to kind of go this. I want both of those arrows to kind of fall into the asymptote or get closer towards the asymptote. So I'm just doing that down here. And I don't know exactly where this graph is going to lead to yet. So I didn't want to go too far. So I just want to have just enough for me to create that behavior around that asymptote. But I don't want to go too far because I don't know yet what's happening on to the right of that asymptote. Okay. Next up, f of 3 is undefined. So it just tells us that there is no point that's defined there. I'm really not going to do anything with this. I just know that at the end of the problem, I'm going to go back and look at my graph. Is there anything at 3? There shouldn't be anything at 3. All right. Put a star next to 6 here. It says the limit does not exist. So this is a very general statement, and everyone may have a different way of interpreting this. So I want to talk about what the options are. So if a limit doesn't exist, your graph can look a number of different ways. I'll give you some options here. One way is you force the graph to have a vertical asymptote. That's fine. That fulfills the condition the limit doesn't exist. Okay. You can also have a graph where the arrows are not headed towards the same y value. So pick any two y values and have the arrows point to different y values. Right? This is also a limit doesn't exist. Right? Here's the third option. You can make the graph head towards 3 and just stop and not pick up any, make it an endpoint. If you make it an endpoint, then that is also a limit doesn't exist, because in order for a limit to exist, I got to be able to have 2 points on both sides. I got to be able to show 2 arrows pointing to the same y value. And if there's nothing for me to describe on the other side of the graph, then the limit doesn't exist either, right? So all these 3 conditions fulfill limit doesn't exist. Now, this is what we cannot do. If I do this, does limit exist here? It does, right? Because but this is what a lot of students do, because I think it still kind of takes us a little bit of time to recognize that a hole with just a hole, the limit still exists. Even though the point doesn't exist, this still fulfills the condition that the limit does exist. So we don't want to draw it this way, because this one would not be in agreement with this, right? This one would be a limit does exist. So you can choose one of these 3 options to graph, but not this one. So because there's multiple ways of doing this, everyone's graph may look a little different and still be fine. So if you want to do a vertical asymptote at x equals 3, that's fine. I'm just going to have my graph purposely point to 2 different graphs, 2 different y values. You can have one lower than the other. You can have this one be lower. So yours may look different from mine. But as long as it's looking like one of these 3 conditions, you're good. Finally, limit as x approaches 6 equals 4. So now I want a limit to exist. So I'm going to put a hole at this order pair. I'm going to just slightly extend my graph on both sides. I want my graph to approach order pair 6, 4 from both sides, but I don't want to commit to that order pair being there. So I'm going to just see if I can make this graph a little bit more connected. So here looks like I'm going to just connect these 2 here. You can stop the graph here, but you're more than welcome to have an arrow exit the graph, So whenever you draw arrows, make sure that your arrows are exiting the graph and not pointing towards the graph. So here's the issue. Sometimes students do this. They would say, okay, limit exists. They would put a hole there, and then they would start doing this here. This may not be a problem because this is exiting the graph, but this one, if I see this, I'm going to follow the graph with that arrow, and that arrow may end up conflicting with another part of the graph that you've already drawn. So if you just have an arrow pointing towards the inside of the graph, this may fail the vertical line test, and that may lose a point. Okay. So whenever you want to draw where limit exists, just do 2 segments, but don't put arrows on either side, because if you draw arrows on either side, I'm going to follow those arrows, and if it conflicts with another part of the graph, then vertical line test may be an issue. Oh, another thing that I see some students do is, let's say there is a limit as x approaches 3 of f of x is equal to infinity. So I see some students do this, where they see the vertical asymptote here. And so students understand that both arrows need to go towards infinity, but the arrows need to get closer towards the asymptote, not further away. So I see some students do this. They would draw it this way. Okay? This would not be the appropriate description of infinity here. So here, this is more like the graph is headed towards negative infinity. But if it's like this, then this is not, it doesn't approach the asymptote, right? If I want to draw the graph with this behavior, it needs to look more like this. So make sure that whenever you draw in an asymptote, that your arrows are getting closer towards the asymptote and not further away. So this is not going to be correct. All right, we have a maybe around, yes, question. Is it okay? -1. Well, that's 6. Oh, you're right. -1. No, thank you. That's a good point. I did not make my graph pass the vertical line test. This should not occur. So there's 2 ways around this. You can either make the graph connect to this point, or you can make the graph have a hole here so that it doesn't, or you can stop the graph on either side and not even get towards this point. But yeah, thanks. Yeah, these should not be in conflict. Yeah, so I think sometimes this may feel the most challenging because everyone may interpret differently. And also sometimes when limit doesn't exist, I think I see some students tend to, want to gravitate towards a hole, which would be a limit does exist, right? So want to make sure that if a limit doesn't exist, that you're actually following one of these 3 categories. Okay, so can we try 8 through 15? I want to just kind of walk around and see if you're making a slight mistake, that I can point those out, and then that can help us. Yeah, help us with more practice. We're gonna get more practice with this, but at least let's just kind of see where we are. And then after your graph is said and done, make sure you go back and convince yourself that you're not going to fail any vertical line test. So no matter where I drop a vertical line, I should not be hitting more than 1 point anywhere on my graph. And then everyone's graph may look slightly different and still be completely correct. Yeah, good point. This is a piecewise function. So we have different functions that are kind of plotted on top of each other. So you have one function that has an asymptote, but there's another function that is defining that point there. So there is no one graph that can ever do this, but this technically is still a function because that point is not conflicting with any other points. That's fine. So yes, here we do the number of points. We do vertical asymptote, we make it n point to this number. Here it's this, so we do want just a kind of so here just have segments that extend from both sides slightly because you know the limit exists. So I have approached the same line. So this is how I started off my graph here. My order pairs, that's easy to plot. No challenges there. Limit as x approaches 7 equals -5. So I know my limit exists. So I like to always start off with a hole and then extend my graph slightly. But I don't want to commit too much into the graph. I don't want to step on other parts of the graph. So I'm just creating what I know is true right around that point. Here, the limit doesn't exist. I can make it a vertical asymptote. I can make it two disconnected graphs. I can make it an endpoint. That's what I did. It's near the edge of the graph, so I just made it an endpoint. And you can either have a hole or a filled-in point here. It doesn't matter. But if you want, you could have the graph go to a different point towards. But we don't want to connect. If we want something on the other side, either make it an asymptote or have it connect to a different part of the graph. Here, the limit as x approaches 4 equals 2. So I'm just finding that order pair and putting a hole there and extending from both sides. F of 6 equals 4, this order pair. There's a vertical asymptote at x equals 6. So this may seem a little bit strange as to, how come there's a point that lives on this asymptote? And the reason that we can do this is because this is a piecewise function. So you have all these different functions that are not related to one another. They're just being plopped onto the same graph. So there's no one graph that can ever do this, where it's going to define a point on the asymptote. But if I have another graph that is defining it here, it is still a function because that point is not conflicting with any other points. There's nothing else that lives on the asymptote, so we can do that. And then here, I want my limit to exist at order pair towards -7, -3. So I'm just going to have my graph do this here. Okay. If you have disconnected graphs, that's fine, as long as there's no failure with vertical asymptotes. Right, so your homework is just the next page, working with these AP practice. I'm going to send out a link where you can check your answers, and I'll be checking these problems tomorrow on these pages. Okay, AP practice 1 through 8. All right, come get your phones. We're on a schedule today. All right, come get your phones. Yep, that works. Okay.
Like this as.
That works.